This is the pre-lab talk for experiment number 10 for Chem 120 lab, electrochemistry. The goals for this experiment are to perform an electrolysis experiment and compare the results to Faraday's law calculations. In part 2 of this experiment, we'll build and observe electrolysis cells with different components and draw conclusions about and explain the overall cell reactions using standard reduction potentials. In part 3, we'll build and observe galvanic cells with different components and draw conclusions about and explain the overall cell reactions, again using standard reduction potentials. And finally, in part 4, we'll explore building a dry cell and optimize its performance by using what we've learned in the previous parts of this experiment. For today's safety pause, we notice that there's a risk of beakers of solution tipping over as we set up the electrodes for each cell and connect them to the power supply or multimeter. Therefore, we must be very careful as we're doing those setups. This experiment also brings the risk of electrical shock, mainly with working with the power supplies used in the electrolysis experiments. It is important to note that a very good rule of thumb for electrical safety is to make all adjustments and set up everything before plugging in and turning on your power supply. It is also important to never touch any exposed metal parts, such as the clamps for the power supply, when current is running through the power supply, namely when it's plugged in and turned on. We also note that our special waste disposal instructions tell us to make sure we collect copper 2 sulfate solution, as it is an environmental hazard. And of course, we always want to make sure that we goggle it and wear flame-resistant lab coats and gloves when necessary. In this experiment, we'll take a look at the building of both galvanic cells and electrolytic cells. Let's take a brief moment to compare the two, which you've probably done already in lecture. In a galvanic cell, we use a spontaneous reaction to push electrons through a circuit. While in an electrolytic cell or electrolysis cell, we're applying a voltage through the use of a battery or power supply to cause a non-spontaneous reaction to occur. In the galvanic cell, the polarity of the electrodes are that the anode is negative, while in the electrolytic cell, the anode is positive. In a galvanic cell, the reason why the electrode has a negative polarity is because electrons are produced there as, in this case, zinc is oxidized at the anode. While in our electrolytic cell, the battery or power supply pushes electrons away from the electrode on the left, which is our anode, which forces it to have a positive polarity. This also means that the cathode in the galvanic cell has a positive charge, since electrons are being used up at that electrode. In an electrolytic cell, the cathode is negative, since electrons are being pushed there by the power supply. In a galvanic cell, we typically like to separate both half cells into separate beakers. In order to complete our circuit, however, we do need to make sure the ions are able to move freely between the solutions. This is why we use a salt bridge that contains an inert solution. In our lab, we'll use sodium chloride that'll allow ions to move freely through between the solutions and avoids charge buildup in any one half cell, which keeps electrons flowing through our circuit. In an electrolytic cell, we need to use a power supply or battery. And this experiment will basically use the power supply. Notice that in our electrolytic cell, everything is sort of in one pot. Therefore, a salt bridge is not necessary. And in the galvanic cell, we don't need the power supply because we're actually producing a voltage with a galvanic cell. There are, of course, many things that are similar between galvanic and electrolytic cells. Oxidation occurs at the anode for both cells, and reduction occurs at the cathode for both cells. Also, electrons will always flow from the anode to the cathode. This occurs naturally in a galvanic cell, but in an electrolytic cell, it is forced by the power supply or battery. Another important concept to review are what we call Faraday's law calculations. This is also referred to as stoichiometry for electrolysis. In case you're wondering, Faraday's laws are relationships between the charge that is passed through an electrolysis cell and the moles of electrons present and the current that flows through the cell. This flowchart helps to lay out these calculations, especially the one that we'll be doing in this lab. If you know the time that you perform your electrolysis experiment, you can calculate the charge that passes through that cell by multiplying the current that passes through the cell and the time that it takes for the experiment to occur. The current is measured in units of amps, which is 1 coulomb per second. And the coulomb is the SI unit for charge. If you multiply then current in coulombs per second times the time in seconds, you get the charge that passes through the cell in coulombs. Faraday's laws also describe the relationship between charge and moles of electrons that pass through the cell. This relationship is facilitated through the Faraday's constant, which is 9.65 times 10 to the fourth coulombs per mole of electrons. Therefore, multiplying the charge by Faraday's constant, or multiplying it by 1 over Faraday's constant, gives the moles of electrons that pass through the cell. Now we want to go from moles of electrons to moles of the metal that we're plating. We can do this by using a balanced half reaction that shows the reduction of the metal cation to the metal solid. In this experiment, we're using copper 2+, where copper 2+ is reduced to copper solid by the addition of 2 moles of electrons for every 1 mole of copper ions. Finally, you can calculate the mass of the metal that is plated from the moles of metal by using the molar mass of the metal itself. You can use this flowchart to help you in your calculations. Although in your report pages, the calculation is stepped out in different items, you can still use this flowchart to follow along. Another important thing to remember is looking at standard reduction potentials. There's a table of standard reduction potentials in the introduction and experimental portion of your experiment. You can use these in part 2 to help corroborate what chemistry is happening in our different electrolysis cells, and in part 3 to calculate a cell voltage. Remember that to calculate a cell potential, you take a reduction potential and add to it the oxidation potential. And that oxidation potentials are typically calculated by reversing the direction of a half reaction, which changes the sign of the potential. Let's discuss a few procedural points. For parts 1 and 2, we need to be able to handle our power supply safely. First of all, it's important to note that we used to use a piece of equipment called a conductivity box, and some still float around the lab. So if you are doing this in person, make sure that you grab a power supply that is labeled as such. As mentioned before, you should make all connections to your electrodes before plugging in and turning on the power supply to avoid electrical shock. You can test your power supply by connecting the two brown leads to each other, turning on the power supply, and measuring the voltage. The voltage should read at about 0.05 volts. Something that you might not see too much in the video lab is that we need to make sure that all of our electrodes are cleaned very well before using. This removes any layers of oxidation that might impede our voltage measurements. In part 1, you can see that if you're looking at the original lab experiment itself, there's room to do 2 trials of the electrolysis experiment. Typically, this is only done if there are serious issues with the electrolysis the first time around, which typically doesn't happen and does not happen in this video. Well, I also wanted to make special note of some difficulty with the graphite electrodes, namely that the graphite electrodes are just simply graphite rods that are put into a holder. Sometimes it's difficult to get the electrodes or the clamps to go around those electrodes. So you should exercise good caution when doing that and be patient. In part 2, it's really important to make sure you make good observations. First of all, the observations are going to be electrode dependent. I use a convention in all of our experiments that I keep the anode on the left hand side of the screen and the cathode on the right hand side of the screen. This should help you when you're making your observations that are electrode dependent. We also will be making some measurements while stirring and without stirring for part 2. Also in part 2, to confirm some of the behavior, we'll put a porous barrier made of filter paper between the 2 electrodes. In part 3, it's important to note that no power supply will be used since we're building a galvanic cell. Using a power supply in the past has led students to make incorrect conclusions and measurements. In the video lecture, you'll get a chance to see how we make the salt bridge, which is an arduous task. But more on that later. I hope you enjoy the video, guys.